Hey there, welcome to another episode of Dominic Does DIY. As always, like, subscribe, and comment down below in order to process that algorithm thing if you find this entertaining or useful. Today we'll be trying to figure out what happened with the new guys circuit. Company just had a hiring blitz and we got a bunch of new guys. Boss comes and asks us to give these guys some basic skills tests to see where they fit, considering the boss didn't want to spend much on salaries and decided to hire all fresh college grads. So you figure a quick, easy test to see if they know some basic electronics is for them to wire up a simple low-side switch, using an NMOS and using that to turn on an LED. No fancy switches or anything. Just when you apply 5 volts to the circuit, the LED turns on. You point them to your random electronics stash of stuff and tell them to have at it. 15 minutes later, you go to check on him, and he is sitting there wondering why the LED is not working. You review his circuit, and while a disaster and overly complicated, it seems to not be wrong. He showed you his original plan, but when he went looking for resistors, he didn't find those bags exactly. But set on using those values, he did some stuff that should have worked based on his schematic he showed you. You look at the original schematic and give approval. A 10K pull-up and a 100K pull-down resistor will turn the FET on. Since he didn't have those, he showed you what he did with what he had to get the 10K and the 100K ohm resistor values. Looking at the schematic of the circuit he actually built, you think highly unnecessary, but whatever. You do the math in your head, and yeah, he knows how to do math. It should work fine, and he pretty much kept his 10K and 100K values. He has 300K resistors in parallel, give you 100K, two 17.2K resistors in parallel, give you 8.6 plus the 1K, gives you 9.6K, close enough to 10K. So his maths look good, and the circuit should work as expected. So you take a look at the physical circuit, and everything physically is connected correctly per the schematic. Right? You have the 2 resistors in parallel going into the resistor in series, and the 3 resistors in parallel, and the gate is connected exactly like it should be. So there's no incorrect wire connection. However, the circuit does not illuminate the LED as expected. So you ask the new guy, you ask him to probe the gate because you want to see the voltage there on the 2N7002 Fairchild FET to get a better understanding of what's going on in the circuit. So he goes in and turns the circuit on and go ahead and puts a voltage probe right there on the gate. So then we take a look at the scope, and I'm just going to go ahead and make this a little bit bigger so we can see it. And when we look at the scope, we can see that the voltage level is at about 1.17, right? It's about 1.17 volts, a little under 1.2 volts. So that's not what we were expecting. What we were expecting was if there's a 10K and 100K resistor, we should be a lot closer to the 5 volt range. But right now we are really low at 1.2 volts. Although NMOSs, usually when we guess these things, we get some rough numbers. We usually say we just need to be above 1 volt to turn an NMOS on. So is it interesting right now of 1, why do we not have 5 volts or close to 5 volts on the gate? And 2, why doesn't the NMOS turn on even though we have greater than 1 volt on the gate? Can you notice the 2 issues with the circuit that prevent the LED from being illuminated? 1, why don't we have closer to 5 volts on the gate of the FET? And 2, why isn't the FET turning on when we are putting more than 1 volt at the gate? Pause the video here if you would like to give it a go, and I will go over the answer in a second. First, let's take a look at the easy one. If we take a look at the resistors and their resistor bands, even though he said he found a quantity of 300 kiloohm resistors, looking at the bands, clearly one of them is only 3 kiloohms, which is throwing off the whole divider series. So instead of setting the gate near 5 volts, as expected, which is this V out, we just relabel that as the gate voltage. So we have our 17.2 resistors in parallel, which gives us the 8.6. We have our R3, which is in series right here with 1K, and then R4, 5, and 6, which are down here. And those are all should be set at 300K. So 4, 5, and 6 in parallel gives us 100K. And when you do the division on that, when our V in is 5 volts, which we can see right here, then our gate should be about 4.56 volts, but it's not. Remember, we got 1.12. So what happened is when we look at the bands, actually one of the resistors, this R6 here, it's actually a 3K. So if we change that to 3K, you can see that that upsets the entire circuit and it knocks our gate voltage down to about 1.17 volts, right, which is exactly what we were seeing on the system. So that's the first issue, is there was a wrong resistor placed there, messing up the voltage divider to give us 1.17 volts instead of the expected 4.5 volts. For the second issue of why doesn't the FET turn on even though we have more than 1 volt on the gate of the NFET, for that we actually have to go look up the data sheet. Remember, this is a 2N7002 Fairchild MOSFET, N-channel MOSFET. So if we go take a look at the data sheet on that, we can see that in the data sheet, what we're looking for is this VGS threshold, and we can see that the threshold on this thing is nominally 2.1 volts. And so because it's 2.1 volts, we know that we got about 1.17 volts, clearly not high enough to actually turn the system on. And to be sure that it's turned on 100% of the time, we should actually make sure that under all circumstances, our voltage is greater than 2.5 volts. That'll ensure that this thing can turn on under any condition, right? So that's the second issue, is our gate voltage just was not high enough to overpass the threshold needed by the FET. So after reviewing this circuit a short time, we grab a pair of cutters and we cut that 3 kiloohm resistor out of the circuit. And lo and behold, when he turns the power on, we can go ahead and see the probe there. And we can see we're right where we want to be, about 4.5 volts. Make this trace a little bit thicker. And because that gate voltage is above the VGS threshold, we go ahead and add another plot. And we'll go ahead and take a look at the current going through our diode here, our LED. And we can see, again, we just make it a little thicker so we can see it. And we can see that we're getting our expected roughly about 20 milliamps going through our LED to illuminate the LED. So the system is working exactly as we want it to, and everything is happy. Thanks for watching, and I hope you enjoyed the video. And thanks to all who have subscribed and shared. I'll see you next time. Have a good one.